This video will demonstrate how to implement the interconnected node options for the graph. Hello, I'm James Helfrich. The graph is not provided in the standard template library. Nevertheless, it is a very useful data structure we use in many everyday applications. There are 4 implementation options. This video will demonstrate how to implement the interconnected nodes option. We have 4 implementation options for the graph. The first is interconnected nodes. Here we have an array of pointers to a graphical node, and every node can point to other graphical nodes. If there is a pointer from one graphical node to another, then there is an edge. The second is a set of edges, where every edge is represented by a source-sink pair, and we have a collection of edges in a set. The third is an array of sets. We have an array of source vertices, and every source vertex has an array of possible destination vertices. If there is a destination vertex for a given source, then that source destination is an edge. And the final is a grid, otherwise known as an adjacency matrix, where the horizontal axis represents the source vertex, the vertical axis represents a destination vertex. If there is a true in a source destination location on the grid, then there is an edge. If there is a false, then there's not. We're going to focus on the interconnected nodes implementation option. Let's take a look at the UML class diagram. Our class is called graph, and it has a constructor and assignment operator, empty, size, and clear, just like you'd expect. It also has add, where I can add a given edge between a source and a sink. I can also remove a given edge given a source and a sink. I can also determine if a given edge exists between a source and a sink. I have a findEdges, and it's going to give me a set of sink vertices corresponding to a given source vertex. And finally, I have findPath. FindPath is going to give me a list of vertices leading from a source to a sink vertex. Now, I have one member variable called vertices, and a vertices is going to be a collection of graphical nodes. How many? N. If I have 10 vertices in my graph, then there's going to be 10 graphical nodes in my vertices array. Every graphical node will have an array of edges, and those array of edges is going to be a collection of pointers to other graphical nodes. Now let's say, for an example, I have my graph of 10 vertices, okay? One vertex has no outgoing edges. This means there's going to be 0 pointers in my array of edges. It's going to consist of 10 null pointers. Another example, let's say a given vertex has 10 edges. In other words, it points to 10 other nodes. Then there's going to be 10 pointers in my array of edges. So therefore, I'm going to have between 0 and n possible references to other graphical nodes. Now, every graphical node is going to refer to a given vertex. And notice how many of the methods in my graph class refer to a vertex. So therefore, I need a vertex class that's referred to by add, remove, isEdge, findEdges, and findPath. And notice graphical node also refers to a vertex. This is probably best demonstrated by example. Here I'm going to have a graph of 5 vertices. So I'm going to start with an object called G, which is going to be a graph of 5, where 5 corresponds to the number of vertices. From the user's perspective, I'm going to have 5 vertices, 0, 1, 2, 3, and 4. From the code's perspective, I'm going to have an array of vertices, and each one is going to be a pointer to a graphical node. And there's going to be 5 graphical nodes, and each graphical node is going to consist of 5 pointers to other graphical nodes. Now, my original vertices on the bottom is going to point, slot 0 is going to point to vertices of 0, slot 1 is going to point to vertices of 1, and so on. Now, from the second row, vertices of 0, there is no outgoing pointers, which means it's going to be filled with null pointers, which means there is no edges currently. Now I'm going to add an edge between vertex 0 and vertex 1. Now, from the user's perspective, the source is 0, the destination is 1, there's going to be an arrow there, 0 to 1. From the code's perspective, I'm going to go vertices of 0, and that's going to be my source, slot 1, which would be my destination, and that 1 is currently a null pointer, but now it's going to point to vertices of 1. I'm going to add an edge between vertex 0 and vertex 3. So my source is 0, my sink is 3. So now I'm going to go to vertices of 0, slot 3, which is currently a null pointer, and now it's going to point to vertices of 3. I'm going to have source 2, sink 1, and vertices of 2, slot 1 is now going to point to vertices of 1. Source 3, sink 2. So vertices of 3, slot 2, currently a null pointer, will now point to 2. vertex 4 to vertex 0, source 4, sink 0. So vertices of 4, slot 0 is currently a null pointer, but now it's going to point to vertices of 0. 4 to 2, 4 to 2, 4 to 2, and add vertex 4 to vertex 3, source 4, sink 3, or vertices of 4, slot 3 will now point to 3. There are 4 main algorithms associated with the graph. The first is isEdge. I want to determine if a given edge exists in the graph. Now I'm going to take a source and a sink vertex. Now remember, my graph consists of a single member variable called vertices, and this can be a collection of pointers to graphical nodes. Now, which graphical node am I going to refer to? Vertices of source. That is going to give me a graphical node. The graphical node has a member variable called array of edges, and that array is going to have a collection of pointers, and I'm going to refer to them by sink. So if there is a pointer there that's not the null pointer, then I have an edge. But if it is the null pointer, I do not have the edge. Therefore, vertices of source dot array edges of sink will tell me whether I have an edge or not. Now this is O sub 1 because I'm going to do 2 array lookups, vertices of source and array edges of sink. The next function is called findEdges. I want to find all the edges leading out of a given source vertex. Now I'm going to say vertices of source, and that's going to point to a graphical node. And then that graphical node is going to have an array of edges. And I want to walk through every single one of those. So I'm going to iterate from the beginning to the end. And what am I going to get from that? I'm going to get a sink, which is going to be a pointer. Now, if this sink is not the null pointer, then I want to insert that sink into my set return. If it is the null pointer, then I'm going to skip it. I'm going to return my set return, which will be all my sink vertices corresponding to a given source vertex. Now, what is the algorithmic efficiency? Well, it's O sub n log m, where n is the number of vertices and m is the out degree of the vertex. Now, let's see why that is. Let's say, for an example, that my given source vertex has no edges leading out of it, okay? Then I'm going to go through all of my array of edges, and there's going to be n of them because there are n vertices, and all of them are going to have the null pointer, so I'm not going to insert anything. Therefore, because I go through n times, that'd be O sub n. Now, let's say that I have n outgoing vertices. In other words, I have 10 vertexes in my graph, and my given source vertex has 10 edges associated with it. Then all my sink pointers are not going to be the null pointer, but rather they're going to be pointed to an actual graphical node. In this case, I'm going to insert n times. And how long does it take for me to insert something in a set? It's log n. So therefore, it would be n log n. Now, what is the out degree of my given graph? Well, its m was between 0 and n. So therefore, my total performance is O sub n log m. Next, I want to add a given edge to my graph. I'm going to get the source and sink vertices. So I'm going to say vertices of source, and that's going to point to a graphical node, array edges of sink, and that's going to refer to a given edge, and that's going to get a pointer to my vertices of sink. Now notice, once again, these are 3 array lookups. Vertices of source, O sub 1, array of edges sink, that's O sub 1, and vertices of sink, that's going to be O sub 1. So O sub 1 plus O sub 1 plus O sub 1 is O sub 1. The final method I want to implement is to want to remove a given edge between a source and a sink. This is going to look a lot like the insert with one important exception. Instead of giving it a valid pointer to a graphical node, instead I'm going to put the null pointer. And this is O sub 1 plus O sub 1, which is O sub 1. Okay, let's take a look at the example of a graph with 3 edges. Let's see if you can draw out the graph from the user's perspective and then also draw out the graph from the code's perspective. Pause the video and see if you can do this. Okay, let's take a look here. I have a graph of 3 vertices, 0, 1, and 2. Notice how there are no edges currently. My graph member variable is going to be a vertices array, 0, 1, and 2, and it's going to point to 3 graphical nodes, vertices 0, vertices 1, and vertices 2. Vertices of 0 are going to point to vertices 0 and 1 and 2, so on. Notice how there are no edges leading out of vertices 0 or out of vertices 1 or out of vertices 2. Now I'm going to add vertex 0, comma vertex 1. Vertex 0 is the source, vertex 1 is the sink, so I'm going to have an edge there. Now, the vertices of 0, slot 1 is going to be a pointer to vertices 1. I'm going to add source 0, sync 2, 0, 2. So I'm going to say vertices 0, slot 2, current the null pointer. There's no arrow leading out of it, and it's going to point to vertices 2. Add vertex 1, comma, vertex 2, so from 1 to 2, and then from vertices 1, slot 2 to 2. And finally, add vertex 2 to vertex 0. Source is 2, destination is 0, and vertex 2, slot 0. You can learn more about the interconnected nodes implementation of the graph in the graph chapter of the C++ data structures textbook.